Welcome. In this video, we are going to do some more with electron configurations, and we are going to focus here on valence electrons and ions. So what is a valence electron? A valence electron, those are your outer electrons, and the definition of what it means to be an outer electron is they're the electrons found on the outermost shell. And I have the word shell here emphasized because it's about the shell, not the subshell, not the orbital. So you want to be looking at the shell number when you're trying to figure out valence electrons. And the valence electrons are on the outside, so they're the ones that tend to, interact with the surrounding world, and they're the things that have, impact on a lot of things like bonding and stuff like that. So we tend to focus on the valence electrons. The electrons that are not valence, we call those the core electrons. They're the ones found on inner shells. So when you're trying to find the valence electron, you want to look for the highest shell number in the electron configuration. So like if you look here with arsenic, here's its electron configuration. The highest shell number is the 4th shell. And you want to look out because there might be several subshells within that shell. So in this case, there's 2 subshells in the 4th shell. So there's 2 electrons over here in the 4s, and there's 3 over here in the 4p. So from this, it looks like arsenic has 5 valence electrons. Notice how these ones right here in the 3D, those get left out. Okay, because they're actually in the 3rd shell. They're actually core electrons. Manganese, over here, its highest shell is the 4s, so it has 2 valence electrons. And again, what you want to notice is that the valence electrons are not necessarily going to be the last ones you write down. So you want to just scan through your electron configuration and look for the highest shell number. And that's your valence shell. Okay, if we look here at sodium, notice its highest shell is the 3rd shell, so it's got 1 valence electron in the 3rd shell. Arsenic has 5 valence electrons in the 4th shell, and then manganese has 2 valence electrons in the 4th shell. All right, so understanding the valence electrons will help us understand ion formation. And there's 2 types of ions. There's cations and anions. Cations are positive, and to form a cation, the metals tend to lose valence electrons. So metals over here on the left tend to form cations. They lose electrons when they form ionic bonds. The nonmetals over here on the right, they tend to gain electrons and they'll form negative ions. Those are called anions. So here's an example of an anion and a cation. So oxygen normally in its neutral form has 8 electrons. It looks like this. When it forms the -2 ion, it gains 2 electrons. Now it has 10, so here's its new electron configuration. Notice how it added 2 electrons to its valence shell. Aluminum, neutral aluminum, has 13 electrons. When it forms a positive ion, it loses electrons. So in this case, it loses 3 electrons. So now it also has 10 electrons. And notice how the electron configuration here is actually the same as that of oxygen. So oxygen gained electrons, aluminum lost electrons. They ended up with the same electron configuration. There's a word for that. We call it isoelectronic. It's where you have the same electron configuration. So we will notice this when you start dealing with ions. You can have some that are isoelectronic, which means same number of electrons. But keep in mind, they still have different numbers of protons. So they did not become the same element. So oxygen's still oxygen because it has 8 protons. Aluminum still has 13 protons. So these things still have different properties, but they do have the same electron configuration. You might also notice that electron configuration is the same as that of neon. So neon is also 1s2, 2s2, 2p6. And so you might remember in regular chemistry something we called noble gas envy, which we noticed that many elements, the ions of many elements, will be isoelectronic with the nearest noble gas. So they'll end up with an electron configuration that looks like a noble gas. We'll find that a lot of the rules we learned in regular chemistry don't always hold true. So this isn't always the case. But it is often the case, which is why we pointed it out in general chemistry. But there are examples where this does not work, so what's better is to just focus on the valence electrons. Okay, so here's an example, titanium. This is the electron configuration for neutral titanium. notice that its valence electrons are in the 4s. So when it forms the +2 ion, it loses these 4s electrons. But at the end, you end up with, 2p6, 3s2, 3p6, and then 3d2. And notice how that is not a noble gas configuration. So the nearest noble gas is argon. It doesn't have anything in the D subshell. So the titanium ion does not look like a noble gas. So again, noble gas envy, as a rule, doesn't always work. So again, focus on the valence electrons, and just keep in mind that metals tend to lose their valence electrons, and non-metals tend to gain electrons in an open valence shell. Okay, so some more practice here. The nitrogen 3-, actually we did that example over here on this page. So N3- is 1s2, 2s2, 2p6. It looks just like neon. Let's look at sulfur. So sulfur normally, and often what I find helpful is to write the neutral version first. So I'm going to write neutral sulfur is 1s2, 2s2, 2p6, 3s2, 3p4, because sulfur is right over here. And the 2- ion, I'm going to add 2 electrons to your valence shell. So 1s2, whoops, 2s2, 2p6, 3s2, 3p6, 3p6. Sorry, that got messy. You might notice that the sulfur ion is actually isoelectronic with argon. Okay, let's look at cadmium. Cadmium is down here. So I can write it out, the full electron configuration. I can also use the noble gas shortcut if I want to. So cadmium, let's use the noble gas shortcut. I'm going to look at the previous noble gas, which is krypton. So neutral cadmium is like krypton, but with, let's see, 1, 2, 3, 4, 5, but with 2 electrons in the 5s and 10 electrons in the 4d. So this is neutral cadmium's electron configuration. The cadmium +2 ion is going to lose 2 electrons from the valence shell. So it's going to lose these electrons. So the cadmium ion is going to look like this, krypton 4d10. And you can really clearly see that this does not have a noble gas configuration, because notice how it's cadmium 2+. It's like krypton, but it also has 10 more electrons in the 4d. So there we go. If you look at lead, you might be familiar from regular chemistry with the idea that some metals can form more than one charge of ion. One example of this is lead. And so let's look at neutral lead to begin with. Let's see, lead is right over here, and it's kind of a big one. So let's use the noble gas shortcut. So here's lead, and the previous noble gas is xenon. So lead is xenon. And then let's look at what row it's in. It's in 1, 2, 3, 4, 5, 6. It's in row 6. So it's xenon, 6s2, and then 5d10, and then 6p2. So that's where lead's electrons are. There we go. So now let's look at the lead +4 ion. So it's going to lose 4 valence electrons. Notice that lead has 4 valence electrons, 2 in the 6s, 2 in the 6p. So when it makes the +4 ion, it's going to lose all of those, and it's going to be xenon 5d10. Lead can also form a +2 ion, in which case it might just lose some of its valence electrons. And if you're trying to make a guess which valence electrons is it going to lose, well, it's going to lose those ones that are furthest away. So it's going to lose the 6p ones. So in the +2 version, it only loses the 6p electrons. So you sometimes see metals having more than one charge down here with these transition metals where there's a D block involved. So like lead's an example, and there's many ions here in the middle like iron or nickel or copper that will form more than one charge of ion as well. Okay, then I'm gonna so that's it for this video, and thanks for watching.